Good morning, dear student. Sorry. Good morning, dear students and friends. I welcome you again in the lecture series of the subject E145, that is Basics of Electronics and Electrical Engineering. See, in the lectures hours, we had solved many sums of the mesh and nodal analysis, and I have also provided you the video lecture in which the important sums of mesh and nodal analysis have been discussed. So in today's topic also, we will discuss some sums regarding the mesh and nodal analysis, right? So it's chapter number 2, and this video is the part number 2 of mesh and nodal analysis sums. So, okay. I have taken this sum from the book of V.K. Mehta, example number 3.16. So let us read the statement. Use the nodal analysis to find the current through 4 kilo ohm resistance as shown in the below figure. So first of all, see whether you have to find the voltage or current using the nodal analysis or mesh analysis. First of all, see. So in this case, we have to use the nodal analysis. It means KCL. Now see, the figure is given. Here there is a current source of 50 milliampere. There is a node A. Between these two nodes, resistance R1 is connected, whose value is 1 kilo ohm. Between node A and B, current source of 30 milliampere is connected. Current is flowing from B to A. Between A and this bottom node, resistance R2 is connected, whose value is 2 kilo ohm. It means 2000 ohm. Now, between B and this bottom node, which is the reference node, R3 is connected, whose value is 2 kilo ohm. And between B and reference node, another resistance R4 is connected, whose value is 4 kilo ohm or 4000 ohm. Again, in the nodal analysis, first of all, determine the principal nodes. First task. So here, this is the principal node A. Why? Because at this node, more than two circuits elements are connected. So in this case, this and this, total 4 circuit elements have been connected. So it's a principal node A. This is also a principal node because at this node, this and this 4 branches are connected. So B is a principal node. And this bottom node is also a principal node because at this point, this R3, R4, R2 and current source are connected together, right? And as per the rule, we have to consider one node as the reference node. So this bottom node has been considered as the reference node, and the all voltages will be considered with respect to this reference node. Okay, now see in the figure, the currents are not given. So first, in the second step, we have to assume the direction of the current and the variable for each and every current. So I let us start from this LHS. There is a current source of 50 milliamps, and let us say this current is I1, which is flowing from this terminal to the A, right? See, I1 is flowing in upward direction, so consider I1 in the upward direction, right? It is given, so don't change it. Then between A and B, I assume that current I4 is flowing through resistance R1, right? Between B and A, 30 milliampere is current is flowing, so from B to A, so let us say this current is I2, it is flowing from B to A, and it is 30 milliampere, and see, direction is given, so don't consider other direction, right? So I2 is flowing from B to A, it is given. Now from A to this reference node in the downward direction, let us assume that current I3 is flowing, right, through R2. Now from a B to this reference node, I5 current is flowing in the downward direction through resistance R3. And from B to this reference node through resistance R4, current I6 is flowing. I6 is flowing. Right, so in the second step, we have considered the branch currents and associated variables related to the branch currents. Right, and our aim is to find each and every branch currents, right, using a KCL. Okay, so now one by one we will apply the KCL for each principal node. So there are actually three principal nodes, A, B and reference, right? But we don't write any equation for the reference node. We write the equations for the principal node A and B. So there will be two KCL equations, right? So first of all, apply the KCL for the principal node A, and again recall the fact that KCL, as per the KCL, summation of the incoming currents at the node will be equal to the summation of the outgoing currents, right? Sigma incoming currents is equal to sigma outgoing currents at each and every node. Okay. So, which are the incoming currents? I1 plus I2 would be equal to outgoing I3 plus I4. I1 plus I2 is equal to I3 plus I4. That's all. Now I1 is already given 50 milliampere. So convert it into amps. So 50 into 10 raised to minus 3 plus I2. I2 is how much? 30 milliamps, right? It is incoming. So 30 into 10 raised to minus 3. Now I3 current. I3, yes. It is what? VA minus reference node's voltage, which is 0. So VA minus 0 upon R2, and R2 is 2 kilo ohm. So VA upon R2, right? Plus I4. I4 is what? I4 is flowing from A to B. So we assume that VA is more than VB. So VA minus VB upon R1. VA minus VB upon R1. Okay. So simplify this, you obtain this. V upon R2 is 2000 ohm plus VA minus VB upon R1 is 1 kilo ohm, so it is 1000. Right, so simplify this, and ultimately you will obtain equation number 1, which is 0.0015 VA minus 0.001 VB is equal to 0.08, equation number 1. There are two unknown variables VA and VB, so there will be two equations, right? Two variables, two equations. Now apply the KCL for the node B. Now summation of incoming currents. Which are the incoming currents? Incoming current at node B is I4, and is there any incoming? No. I2 is outgoing, I6 is outgoing, I5 is outgoing, right? So incoming is only I4. So I4 would be equal to outgoing I2 plus I5 plus I6. That's all. Now write the equations in terms of the nodal voltages. So I4. Please pause this video and try to write the equations. I4. I4 is what? I4 is flowing from A to B. So VA is more than VB. So VA minus VB upon 1000. VA minus VB upon R1. And R1 is 1000 ohm. Plus I2. I2. Yes, I2 is given. It is flowing away from the node B, outgoing for the node B. So I2 is 30 milliamps. So 30 into 10 raised to minus 3 plus I5. I5. It is VB minus 0 upon R3. So VB upon R3 is 2 kilo ohms, so 2000. So VB upon R3, so VB upon 2000 plus I6. I6 is VB upon R4, and R4 is 4 kilo ohms, so 4000. So VB upon R4 and VB upon 4000. So you obtain this equation, simplify this, and ultimately you will obtain equation number 2, that is 0.001 VA minus 0.00175 VB is equal to 0.03. Now there is equation number 1 and there is equation number 2. Arrange those equations in terms of the matrices. So this is the coefficient matrix, this is column vector VAVB, and this is the RHS of equation 1 and equation 2, right? So this is the matrix multiplication. So VA and VB would be equal to what? Take this matrix on RHS, so take its inverse, and to 0.08 and 0.03. So it's inverse of this matrix into this will give you this value. So VA would be equal to 67.69 volts and VB would be equal to 21.53 volts. So VA and VB are obtained using the nodal analysis. Once the nodal voltages are obtained, you can find the branch current. And in this case, I have to find the current through 4 kilo ohm resistance. So 4 kilo ohm resistance current is I6. So I6 is what? I6 is VB upon R4. VB minus 0 upon R4. So VB is there 21.53, 85 upon R4 is 4000. So answer is obtained 5.384 milliamps. It is in milliamps. So this is the answer. Okay, so this was the application of the nodal analysis or KCL. Next. This sum is also taken from the book of V.K. Mehta, page number 129, example number 3.17. For the given figure below, find the voltage small v and the current through 2 ohm resistance using the nodal analysis. See the figure. This is slightly different figure. There is a battery of 6 volt, here positive, negative. Then there is a resistance of 1 ohm, and across the resistance there is a voltage drop of a small v volt, right? And that we have to find the small v voltage across the 1 ohm resistance. There is a principal node A. Between node A and this reference node, the 2 ohm resistance is connected, and here this rhombus shows the control source, and inside the rhombus there is positive and negative sign. So it's a voltage source whose magnitude is what? Phi into small v. Phi into small v. Where is small v? This is the small v, voltage across this 1 ohm resistance, right? So this is what? Voltage control voltage source. Why? This is a voltage source, right? Because it is positive and negative, so it's a voltage source. Okay. And voltage control, it means its magnitude is being controlled by which factor? Phi into V, right? So its magnitude is phi into V, where small v is the voltage across 1 ohm resistance. So voltage across 1 ohm resistance will decide the magnitude of this voltage source, That's why this rhombus is called, or it means this voltage source is called as the voltage controlled voltage source. It is a voltage source, but its value is controlled by another voltage. Which voltage? The voltage drop across this 1 ohm resistance. That's why it is VCVS. Now between A and B 3 ohm resistance is connected, between B and reference 4 ohm resistance is connected, and between B and reference this negative positive 8 volt is connected, battery is connected. Okay, now step number 1, first of all identify the principal node, whether right, in case of a nodal analysis, and in case of mesh analysis identify the meshes. So in this case this is a principal node because at this node this and these circuit elements are connected together. This is also a principal node because at node number B this and this circuit elements, 3 circuit elements are connected. So more than 2 circuit elements are connected means it is a principal node. So A and B is the principal node and this lower is the reference node. It is also a principal node, but it is considered as the reference node. One node should be considered as reference node. Okay. Now see, in the nodal analysis, as per the theory, we require the current sources, right? So we use the source transformation, using which we can convert voltage source into the current source. But in case of when the control sources are given, voltage control voltage source, voltage control current source, current control current source, it means when the control sources are given, at that time it is not advisable to convert the voltage source into the current source. So it means, in short, when the control sources are given, at that time it is not advisable to use the source transformation, right, in which we convert voltage source into the current source. It is because, suppose see, in this case this voltage source is in series with this resistance, right? So this voltage source can be converted into the current source. But if you do this, then the voltage across this 1 ohm resistance will be changed, and as a result this will also change, right? So we will not obtain the perfect answers, right? So in the bottom line is, when the circuit contains the control sources, right, at that time when you want to use the nodal analysis, at that time it is not preferable to convert the voltage source into the current source, right? And yes, remember, if the circuit does not contain any control source, right, if it does not contain any controlled source like voltage source, control current source, current control voltage source, etc., it does not contain any control source, then you can easily convert the voltage source into the current source and you can proceed further to solve the sum, right? Please remember this basic fundamental. Okay, so now again in the second step, for each branch, identify the variable related to the current. So let's start from the LHS, not LHS, from the left hand side. 6-volt battery. So current will be flowing in upward direction, and let us say current I1 is flowing, and I1 will enter into node A. Between node A and B, I3 will be flowing. Now in this branch, see, here there is a positive, here there is a negative, so obviously current is flowing in upward direction, and let us say this current is I2. Node B, the current is flowing in the downward direction, that is I4, right, through 4 ohm resistance. And yes, this bottom node is a reference node. Okay, now one point is certain, that see, potential of B is already given, VB. VB is what? Point B is connected with the negative of the battery, right? So VB is what? Minus 8 volt. VB is already available. VB is minus 8 volt, because point B is directly connected with the battery. There is no intermediate resistance. There is no resistance which is connected between battery and this node B. B is directly connected with this battery. So potential of node B is what? Minus 8 volt, right? Now apply the KCL at node A, right? So summation of incoming currents is equal to summation of outgoing currents. Incoming current is what? I1 and I2, and outgoing is I3. So I1 plus I2 is equal to I3. Okay. Now pause this video and try to write the equations of I1, I2, I3 in terms of the nodal voltage VA. So yes, what is I1? So see, I1 is flowing from this battery, this source, 6 volt, to the VA. So obviously the potential of this battery is higher than potential of node A, that is VA. So what would be the equation of I1? Yes, I1 would be equal to 6, right? This potential 6 minus VA upon 1 ohm resistance. 6 minus Va upon 1 ohm resistance plus I2, right? I2, yes, again I2 is flowing from uh, this node to Va. So obviously the potential of this node, this is higher than Va. And what is the potential of this node? It is plus phi into small v. So phi into small v minus Va upon 2 ohm. Phi into small v minus Va upon 2 ohm. It is equal to I3. I3 is flowing from A to B. Potential of B is VB. So VA minus VB upon 3 ohm resistance. VA minus VB upon 3 ohm resistance. Right. So this is what 6 minus VA. This is pi V minus VA upon 2. VA minus VB is what? Minus 8. Minus 8. So VA minus 8 upon 3. So it would be VA plus 8 upon 3, right? Simplify this. So it would be this. It is VA plus 8 upon 3. Simplify this and this. You obtain this equation. 20 minus 11 VA plus 15 into small v, it is equal to 0. Right? But recall the fact that small v is what? This small v is what? Right? It is 6 minus VA. See small v. It is the voltage drop across 1 ohm resistance. Right? So this small v is what? This 6 minus VA. 6 minus VA. So it is 6 minus VA. So in this equation, replace small v by 6 minus VA. So this equation would be 20 minus 11 VA plus 15 into small v is a 6 minus VA, it is equal to 0. So simplify this. So this and VA obtained is 4.23 volt, 4.230 volt. So potential of node A is 4.230. VA is this. Now what is our task? Yes, voltage small v and current through 2 ohm resistance. So small v we have to found, VA is found. So small v is equal to 6 minus VA. So 6 minus VA. So it is 1.77 volts. So this is the first answer. Small v is found, right? And the current through 2 ohm resistance. Where is 2 ohm resistance? This, right? So I2 is to be found out. So I2 is what? I2, it is phi into small v, phi v minus VA upon 2. Phi v minus VA upon 2. So phi into V is 1.77 minus VA, it is 4.23 upon 2. Right, so this into this minus 4.23 upon 2, so I2 is 4.62 upon 2, so it is 2.31 ampere. So this is the answer number 2, right? So I2 is 2.31 ampere. And yes, you can also find the magnitude of the voltage control voltage source. It is what? Phi into small v. So phi into small v, phi into 1.77 will give you the magnitude of the voltage control voltage source, which is shown by the rhombus, right? So okay, so this is all about the part 2, which was dedicated to the sums of the nodal analysis. Alright.